Hi, Syed. Morning.
Good morning.
Can you hear me properly?
Yes, but I don't see you.
Okay, I'll be back in a minute. I just need to grab something.
Okay.
Okay, sorry for the delay. Hi, everyone. Let's start with some questions if there's any. Oh, yeah. Oh, no. Yeah, okay. Okay, yeah, sorry about the delay. Let me turn off the waiting room 1 second. How do I do this? Yeah, there. Any questions before we start? Let me just trying to see as many of you as possible, but not many people have their video on. It's the usual suspects that have their video on, but the majority remains anonymous. Okay. Hi, everyone. Okay, so we're racing to the end. We're jumping. We're approaching the edge of the cliff. Any questions? But the good thing is that you don't have a final exam, right? Normally at this time, if it wasn't COVID era, you would all be getting extremely stressed out because of finals. So you should at least be happy about that. All you have to stress out about is a small assignment. No questions? Silence, total silence. I'm not going to start until there's one question.
Are you gonna whistle for us at the end of the on the
Yes.
last lecture?
Well, I don't know. I mean, I've been, this whole class is like one long performance by me, and then you want another one. So maybe if you guys can arrange your own contributions, maybe I'll contribute too. If you want to have a talent show, you should elect, the leader of the talent show, and you should have at least I don't know, 5 people, and then I'll join.
Yeah, we'll start
That's your
planning right
minimum.
after the lecture.
we
Yeah,
can do that.
for sure.
You need a 5 minimum, and then I'll join.
All right.
I'm not gonna go on alone.
Guys, I don't have a talent. This is a problem.
I can debate.
That's,
I can
At the
stare
same
into
time
the
while
void.
Marco is whistling.
I would like to see not only debating, but debate impressions. Debate impressions. I want you to debate like certain famous people, and without telling us who it is, and then we have to guess who the debater is. Okay. Any questions besides these talent questions? Okay. Let me start.
Morgan, did you have a question?
I actually had a question about the quiz we did last Tuesday.
Yeah.
There was some confusion going on in the chat about the fact that for the first question, there was no constraint on the dimension of V being.
Yeah, that's right. So there was a little mistake in my question.
Okay, and there was also a couple questions about the second question. So only the first part was right, and there were 2 other options at the bottom. People were a
that
little
question was perfectly fine. It's just that the setting for the quiz was that it thought that certain answers were correct when they weren't. So I just corrected that, and so the mark that you got now should be the correct mark.
Okay, thank you.
You're welcome. Okay, so I want to go over today the Jordan canonical form, and I want to just approach it from the beginning, starting again, filling in some details and giving a slightly different point of view. 1 second, I just need a file. Which I'm going to open in a moment. Okay, so the first thing that I just first I just want to review about upper triangular matrices, or matrices in triangular form. So putting a linear operator into triangular form. So this means that when you look at the operator, you'll have potentially non-zero entries along the diagonal and above it, or below it. That's another way of doing it, but zeros beneath. Okay, so notice that what this means is that E1 is sent to itself. So E1 is an eigenvector with eigenvalue, whatever this lambda is, lambda. Okay, and E2, let me just move this back to anything. So E2 is sent to a multiple of itself, but not just that, also some multiple of the previous basis vector. And similarly, this is how they all work. So E4 will be sent to a multiple of itself plus something times E3 plus something times E2 and something times E1. Okay, so this is it's not the ideal case. It's not telling you exactly how the operator is behaving. Well, I mean, it's not putting it into a very simple format, but at least it's somewhat organized, that each basis vector is sent to itself plus the previous. Okay, the point is that, you know, if you ask yourself the question, is it possible to put any operator for any vector space into this form? Okay, right away, because of what's happening for the first basis vector, you must know that the answer is no, that it's not possible, because some operators do not have eigenvectors at all, right? Because the field is not allowing it. Like, for example, a rotation, you know, a rotation in the plane is always going to take a vector to a vector which is not linearly dependent to it, which is not a multiple of it. You know, unless the rotation was just 360 degrees, if it was the identity operation. So if the field is not the complex numbers, then you do not have necessarily eigenvectors. You might have plenty of eigenvectors, but not necessarily. And so, you know, one of the requirements to put it into triangular form is to have an eigenvector, and that's not always possible. Okay, but, you know, over the complex numbers, any operator can be put into this form for a finite dimensional operator. Okay, and the proof of that is explained very, very clearly and concisely in the textbook. But let me just review it for a second. Okay, so the proof is by induction on the dimension of the space. Okay, so in other words, we're going to assume, you know, it's obviously true for 1x1 matrices, right? And then for 2x2, we're going to assume that it's true for the lower dimensional cases, and we'll prove it for 2x2 and so on. Okay, and the first step is not surprising. If you look at the form of the matrix, you need to find an eigenvector. So first step, so suppose if the dimension is greater than 1, let's say, let lambda be an eigenvalue. Okay, this is guaranteed to exist since the field is equal to C. Okay, and then the idea is supposed to be the following, that I want to separate off, basically what I want to do is, so the strategy is that I want let E1 be the eigenvector, be an eigenvector with eigenvalue lambda. So let me just draw it here, E1. Okay, and what I want to do is I want to somehow separate off the rest of the space, I'll call it U, and U plus the span of E1 should be all of the vector space V. So yeah, so the idea is that I want to take my eigenvector and somehow split it off for the rest of the space. So I want to find some subspace which which is separate from E1, which is one lower dimension, or at least one lower dimension. It could be much smaller. And then, so I want to find an invariant subspace. So we want to find an invariant subspace U, where we can use the induction, and we can say that the operator on the rest of the space is upper triangular. So somehow the idea is something like this, that we want to somehow, once we find this eigenvalue, we basically want to break the matrix up and focus on this piece, okay, which is one smaller, and we want to show that that is upper triangular. We want to be able to prove, we want to be able to choose a basis for which that is upper triangular. Okay, so let me just proceed with that. So the idea is that if E1 is an eigenvector, this means that E1 is in the null space of T minus lambda times the identity. So this means that we now have an operator. So this operator is a special operator that we now have. Like initially all we had was T. Okay, and then we said, okay, we're over the complex numbers, so T has an eigenvalue, and therefore it has an eigenvector. It could have many eigenvectors for that eigenvalue, but it has at least one. Okay, and so what that means is that the null space of T minus lambda I is non-zero. But that means that T minus lambda I is not an isomorphism. So we don't know about T. T could be an isomorphism. T might not have a null space, okay, and it might be an isomorphism. But T minus lambda I is guaranteed not to be an isomorphism, and it has a non-trivial, a non-zero null space. But that means that it has a non-zero range as a result. Has a non-zero null space, and therefore non-zero range. And therefore the range is not all of V. Okay, so because of the existence of the eigenvalue, we get an operator that has a null space and it has a range. That null space is interpreted as eigenvectors. It's eigenvectors for eigenvalue lambda. Okay, but the range is something else. And because these are operators, they go from V to V. The range is a new subspace, and that's the subspace that we're going to use to do the induction. That's the subspace that you have to check. So let U be the range of T minus lambda I. Then observe that U is invariant by T. So in other words, if V is in U, or let's say if u, little u is in u, i.e. u is equal to t minus lambda times v for some v, then t u is equal to t minus lambda v is equal to t minus lambda tv, which means that tu is in the range of t minus lambda. Okay, so the right. So so this is an invariant space. So therefore, we can restrict t to u, to this smaller space. Okay, and so then we can use the induction. So by induction, there exists a basis. Let's say, what does he call it in the book? U1 to UM. For u, such that t restricted to u is in triangular form. Okay, so then we need to kind of put this together. So we need to kind of create a basis for the whole space. So let's just extend the basis. So extend this to a basis. You could randomly do this. Extend this to a basis u1, um, v1, vn of v. Okay, and then we can just check whether this is putting it into the right form. So if we apply t to, let's say, u1, this is going to be the same as t restricted to u applied to u1, and that's an eigenvector. You know, some number times u1. Okay, t u2 is going to be t restricted to u applied to u2, which is some multiple of u2 plus some multiple of u1. So far, so good. So that's going to be in upper triangular form for all of the u's, and then we just need to check the v's. If I take t vk, sorry, I have v, curly v's and straight v's, t vk, this is going to be, if I just rewrite it, t minus lambda plus lambda vk. This is t minus lambda vk plus lambda vk. Okay, and so what I see is that I get a multiple of vk plus something in capital U. This is in U. This is a multiple of vk. So this is going to be the inside the span of u1 up to um, which means that it's going to be a combination of the previous basis vectors. Okay, and so this puts it in the right shape. So you end up with a matrix that looks like this. In terms of the u's, you have some upper triangular matrix. And in terms of the v's, you get a multiple, v1 is sent to a multiple of v1 plus a bunch of possible stuff of the, combinations of U. V2 is sent to a multiple of itself, and actually it doesn't have any multiples of V1, but it has all this other stuff. Similarly here. Okay, so in particular, this matrix is triangular as needed. Okay. So any questions about this basic fact? So over the complex numbers, any matrix can be put, any operator can be put into this triangular form. And what I want to get to right away, just an immediate consequence of this, okay, is that if we call the diagonal entries lambda 1 up to lambda n, so this is lambda 1, this is lambda 2, and so on, okay, then we have a polynomial that kills the operator. We can just look at this and we can write down right off the bat without any additional work a polynomial that kills the matrix, and that polynomial is z minus lambda 1, z minus lambda 2, up to z minus lambda n. So this is called P of z car, the characteristic polynomial. The characteristic polynomial annihilates t, i.e. P of t is 0. This is not necessarily the minimal. It's not necessarily the minimal polynomial. It might be if you're lucky, but usually oftentimes the minimal polynomial will be smaller. I shouldn't say that usually it'll be smaller. Usually they're equal, because if you choose a random matrix, then these numbers, all of these numbers, if you choose it randomly, all these numbers would be distinct. And then the only way that a polynomial could divide a product of distinct linear factors is if it was that polynomial. So, no, excuse me, sorry, what I said is not right, but we'll, yeah, we'll get to that in a second. Sorry, I just said something that was inaccurate. Just ignore that until later. All I'm saying is that the minimal polynomial divides this characteristic polynomial, but it's not necessarily equal to it. Okay, so the question is why. There's a very simple reason why this thing works. So, so if let me just write it out. So here, so if I take t minus lambda 1, t minus lambda 2, product all the way to t minus lambda n. Okay, why does this combination kill? Why is this equal to the 0 operator? So to see why t minus lambda 1, t minus lambda n is equal to 0, just apply it to each basis vector. Okay, so if I can show that this product kills all of these basis elements, u's and the v's, then I would have shown that this operator is 0. So why does it kill u1? Well, that's easy, because there's a t minus lambda 1 here, that the t minus lambda 1 will kill u1. u1 is an eigenvector. Okay, and it doesn't matter that the t minus lambda 1 is at the front, because I can just, these all commute, so I can move this to the back. That will hit u1 first, right? And it will kill it. Now, what about u2? Okay, so if you take u2, then there's a t minus lambda 2 here. The t minus lambda 2 will hit u2, and what will it do? Well, t u2 is a multiple of u2 plus something smaller, some multiple of u1. So the fact that this t minus lambda 2 is present, that will hit u2, and it will produce exactly something previous to u2. It will produce a linear combination of the previous basis elements. So this t minus lambda 2 will act on u2 and will convert it into a u1. And then this one is present here, and so this will kill the u1. So this one basically strips off the multiple of u2, and this one kills the result. Okay. Similarly, for u3, there's going to be a t minus lambda 3 that will strip away the multiple of u3 and give you something which is a combination of u1 and u2. Then when we apply t minus lambda 2, it will strip away from the u2 component, whatever multiple of u2, and it will leave only u1 stuff. And then this t minus lambda 1 will kill anything that's left over. So in this way, you can see, like, even if you start at the end, take vk, the last vk, t minus lambda n will give you something in the previous v's and u's. And then the next, the next factor in this product will keep stripping away, whatever multiple you have of the current basis vector and give you only previous stuff. And that previous stuff is going to be passed on to the next factor and then killed. Okay. So what I'm claiming is that when you put something into upper triangular form, it becomes completely clear that the polynomial that you make from the diagonal entries kills t. So this is sometimes called Cayley's theorem. Is that the characteristic polynomial applied to t is equal to 0. And all I'm saying is that upper triangular form gives you a very easy proof of this fact. Now, the cool thing about this theorem is that note that if t was over the real numbers, okay, then you wouldn't necessarily be able to put t into upper triangular form. We may not be able to put t into upper triangular form over R, but we can over C. Okay, and then then we have a p car and p car t is equal to 0. And the point is that this polynomial will kill the operator no matter whether we think of it as an operator over C or over R. I mean, it's an identity that the operator satisfies. So if the identity is satisfied over the complex numbers, it will automatically be true over the real numbers too. So this is the Cayley's theorem is something quite general. It doesn't it holds even for operators over the real numbers. I wanted to mention some other comment about this. Oh, yeah, of course. The important thing to remember is that the other comment I wanted to make is that this gives a good upper bound for the degree of P min. Okay, because before what we did was we took 1 t squared. We produced all the way up to t to the n squared. T to the n squared. Yeah. So we took many powers of t, so that the total number of operators exceeded the dimension of the space of operators. And so these are linearly dependent. So this argument gave us a polynomial of degree less than or equal to n squared, right? So that was a really huge polynomial that would kill t. And now what we get, so with the above argument, we get a polynomial of degree n. Okay, so we know that the minimal polynomial is maximum degree n. Forget about n squared, that's unnecessary. Okay, and all right. Okay, but let's okay, but let's continue. So all of this so far is about upper triangular form. And that was a good way to get this characteristic polynomial and to get a bound for how big the minimal polynomial could be. Okay, but now once you've found one of these polynomials, so once we have a polynomial p of z such that p of t is equal to 0, we can apply the decomposition theorem. Okay, and what the decomposition theorem says is that V, the entire vector space, which is the null space of P of t, let's say of t minus lambda 1 to the, I just want to use the same notation that I did before. 1 second. N1 all the way to t minus lambda k nk. So suppose that our polynomial is t minus lambda 1 to the n1. Let's say we factor it over c. And we get a product of linear factors, lambda 1 up to lambda k, to various powers n1 up to nk. Okay, so this means that if I look at the null space of this product of monomial factors, okay, that's going to be the whole vector space. And the decomposition theorem says that this vector space breaks up as a direct sum of generalized eigenspaces. So V is the null space of t minus lambda 1 to the n1 direct sum all the way to the null space of t minus lambda k to the nk. And this is called the generalized eigenspace associated to eigenvalue lambda 1. And similarly, we have these generalized eigenspaces. So the key thing that we want to prove is that we can break up V in terms of these generalized eigenspaces. Okay, and then we can restrict our attention to a single generalized eigenspace and choose a basis putting t into Jordan block form. Okay, so this is the chain of logic. So we need that polynomial. Ideally, you take the minimal polynomial, but even if not, then the decomposition theorem will still hold. It doesn't matter. And then we need to prove this theorem, which is what I'll do after the break. And this theorem will allow me to decompose the vector space into these pieces. Each piece will be basically a lot simpler because that piece will be associated to a single eigenvalue, and it will have basically one important operator. That important operator is t minus lambda, and that will be a nilpotent operator. And we'll just analyze its behavior like the way that we did with the lemmings falling off the cliff. That will tell us how to pick the longest lived elements inside each of these pieces, right? And then we can check that it's in Jordan form. So that's the chain of logic. Let me just make sure that I'm not forgetting something. Okay, so we just need to prove this decomposition theorem, and then I'll go over again the way that we pick the vectors so that everything is in standard form. Okay, so any questions about this? We're going to have a break now for 10 minutes, and then at 12 you'll have a 6-minute long quiz at 12 o'clock.
So Omar has a question.
Yeah, go ahead.
Just to make sure. Can we create what's it called? A basis of eigenvectors for the vector space for every vector space for every operator over C?
No. Okay.
No.
No, because yeah. So the problem is that there is a phenomenon, right, of these generalized eigenvectors. Okay, so the point is that over C you are guaranteed to have one eigenvector associated to each. Yeah, so over C the idea is you try to find an eigenvector. You will always find one eigenvector, but you may not be able to have a basis of eigenvectors because of the fact that you have this cyclic behavior. So you will have some vectors that are not killed by t minus lambda. Those would be eigenvectors, but they're killed by t minus lambda squared or t minus lambda cubed. Okay. Basically, think of it like this: that for every lambda, for every possible lambda, you're looking for the null space of t minus lambda. You're looking to find a vector that is in the null space of t minus lambda because those are your eigenvectors. And depending on lambda, you're going to have a certain number of eigenvalues, and associated to each eigenvalue, you might find at least one eigenvector. Okay, and again, the reason is because you're over the complex numbers, so the polynomial that kills t will have zeros, will have linear factors, and so t minus lambda is going to have at least one element of its null space. But the problem is that you have vectors that are sent to eigenvectors. Yeah, sorry, I just explained it several times last time. That's why I'm kind of I think I'm probably tired of explaining it, but it's okay. I'm going to do it after the break in again, maybe in a different way that might be helpful.
Oh,
okay.
No, it's fine.
Okay, so we have a break at 12 o'clock. You have to go into Quercus and start your quiz. We'll be back at 12:06 at 12. 06. Okay. Are we back? What happened to everyone? Oh, there they are. Okay, so all right, so let's go through this carefully. So we want to prove this decomposition theorem. So once we have a polynomial that kills the operator, we factor it into linear factors to various powers. And then the claim is that we can separate them out. Okay, and for this, I'm going to need a lemma, a couple of lemmas. And the first lemma is one that we showed already. So there was a lemma from before, which said that if you have, let me just get the order right. So if we have U, V, and W, we have T from U to V and S from V to W. And if the null spaces of both of these finite dimensional, of course, you could just assume that all three vector spaces are finite dimensional. That's okay. That's the setting that we're in anyway. But I'm going to use this fact that the null space of T and the null space of S is finite dimensional. Then, so if we have this data, then if you want to figure out the dimension of the null space of the composition being TS, ST, then it's going to be the dimension of the null space of T plus the dimension of the intersection. Sorry, I made this too big, just as I did last time when I wrote this. The intersection between the null space of S with the image of T, or the range of T. So basically there's two ways that ST could kill a vector. Either T kills it directly, or T passes it on to S, and then S kills it. That's what this is saying. That you have the vectors that are killed directly by T, and then S has nothing to do, or the ones that are sent by T into the null space of S. Okay, and a corollary of this is that, let me just, this doesn't require any proof, but it's just an interesting way of phrasing it. It's that the dimension of the null space of ST is less than or equal to the dimension of the null space of S plus the dimension of the null space of T, where equality holds exactly when, you see here, I have the dimension of the null space of T and the dimension of the null space of S, but it's not really a null space of S. It's the part of the null space of S which is inside the range of T. So the equality holds when the null space of S is contained inside the range of T. When the null space of S is contained inside the range of T. Okay, so when you compose operators, the null space dimension doesn't just simply add, there's an inequality. The null space of the composition is less than or equal to the null space of S plus the null space of T. Okay, so this is just a useful, obviously this lemma is going to be useful because I have here a product of operators, T minus lambda 1 to the N1 multiplied by T minus lambda K to the NK, right? And I'm interested, V is the null space of the product, and I want to decompose those, right? And so that's why understanding how the null space of a product relates to the null space of the individual pieces is an important piece of information. Okay, now I started the proof of the decomposition theorem, but let me just start again. So we want to show, so we'll define, let Wi be the null space of T minus lambda to the lambda I to the Ni. And so we wanted to show that V is W1 plus WK, I guess. That's what the theorem says. Now, the first step, I'm going to show that the right-hand side is direct, meaning that I want to show that these null spaces are linearly independent. The null space of T minus lambda I to the Ni are linearly independent. Or in other words, if we have a sum of vectors, W1, if Wi is inside big Wi and W1 plus all the way to WK is equal to 0, we want to show that each Wi is equal to 0 separately. So this proves directness. Okay, so this is a part of the proof, this first step. This is completely analogous to the fact that we showed before, which is that if you have two eigenvectors with different eigenvalues, then the two eigenvectors are linearly independent. Here what we're trying to show is if you have two generalized eigenvectors with different eigenvalues, I should have said that here somewhere, sorry, with lambda I distinct. That's the whole point of the decomposition. I want to decompose it according to different eigenvalues. So yeah, so this is the theorem that we want to show. We want to show that sorry, in part one, we want to show that generalized eigenvectors with different eigenvalue are linearly independent. That's the statement that we want to show in part one. Okay, so so we start with W1 plus WK is equal to 0. And what we're going to do is we're going to show that each one of these is 0 separately. To show that I is equal to 0, we're going to apply the product of T minus lambda j to the nj for all j not equal to I. We're going to apply the killers for the other eigenvalues, not the eigenvalue lambda I. So we'll call this operator Si. Okay. Now, if I apply Si to W1 plus WK, Si is going to kill everyone except for the one that I'm interested in. I'm going to get SIWI. Okay, because it has all of the things that kill the W's. Remember that the W's are the nulls, the Wi are the null space of T minus lambda I to the Ni. So because I have all of the ones except for the one at I, then this will kill all these vectors except for the Wi vector. And because this is equal to 0, I get this, this equality. Okay, so now what I want to do, oh, sorry, what did I do? Am I okay here? Yeah, okay. So to conclude Wi is equal to 0, we will invert Si on Wi. So we're going to show that the operation that Si determines is actually invertible on the space where Wi is living. Okay, this makes sense because yeah, if you think about it, so note that Wi is invariant for Si, right? So why is that? Well, Wi, what is it again? It's the null space of T minus lambda to the Ni. This is an invariant subspace for T, and it's definitely an invariant subspace for the identity. So it will be, this Wi is an invariant subspace for T and for the identity and for any powers of this. So that means that Si automatically will send Wi to itself, right? And we have an equation here that says Si Wi, this element, Si Wi is equal to 0. So all I need to do to kind of get rid of the Si is to prove that it's invertible on that subspace. So Si restricted to Wi is invertible. Okay, so why is that? So I'm going to separate this part of the proof off from this. So an aside is this lemma, which is to show the invertibility of this thing. Okay, so so if S is a linear operator, on W, and S minus A to some power is equal to 0, then S minus B is invertible on W for all B not equal to A. This is a very useful lemma in general, but I'm going to use it for this theorem. So if you have an operator whose A shifting it by A times the identity, if that becomes nilpotent, okay, then that means that S minus A is definitely not invertible because it has a power which is 0. However, if I take S minus B for a different value, B, this is A and B are in the field. And this means, just to be precise, this is multiplied by the identity. Okay. So the proof of this, there's a very clever proof of this. So let me, it's basically, I organized some of the assignment questions so that this would not be too surprising to you. But so we'll first show for B equals 1 and for A equals 0 and B equals 1. These are two elements of the field which are definitely different. Okay, and we're going to show that so if S to the n is equal to 0, then S minus 1 is invertible. So first I'll show it for these particular values. Okay, and the clever proof is like this. It uses the geometric series identity. It says that if you take there's this yeah, there's this geometric series identity which goes like this, that if you take, let's say, 1 minus s times 1 plus s squared plus s to the n minus 1, then what do you get? The first term is just going to repeat, you know, when I use the first summand on the first factor, I'm going to get, you know, I'm just going to get this 1 times the the second factor. So this term is coming from this times this. Okay, but then I'm going to have minus s times the same thing. Okay, and you can see what's happening. S cancels with s squared cancels with s squared, and so on. And then you'll have this cancels with this, and this term here. So then you'll get 1 minus s to the n. And so this is a typical identity, which you probably learned in high school, but s to the n is equal to 0. And so what you get is that 1 minus s has an inverse. Here it is. So this means that 1 minus s inverse is equal to 1 plus s plus all the way to Sn minus 1. So it's invertible. Okay, so so that's it. So we have two values, 0 and 1. S to the n is equal to 0, but that means that s minus 1 is invertible. Oh, I should maybe just say, so s minus 1 is just the negative. Okay, so now how do we show it in general? In general, we have to show for general A and B, let's use a little identity which expresses s minus b in the following way. It's like this. So if I take s minus a, I want to write s minus b in terms of s minus a, like this. So I'll take like this, 1 minus b minus a times a minus b, and this should be s minus b. So this is going to give b minus, you see how this 1 is really like b minus a divided by b minus a. When I subtract this, the a's will cancel and I'll get s minus b over a minus b, and then this will kill that and I'll get s minus b. So the point is that we're getting, yeah, we're getting our two operators. So yeah, you could think of this as being like s tilde yeah, so I'm just saying that you see here, this is like an operator minus 1, and this is just the operator. So you can pretend that that s minus b plays the role of s here. So yeah, this is the, let's see, what have I written here? Right. So one minus. Okay, yeah. So here the idea is that if s minus a to some n, right, is equal to 0, then 1 minus this thing will be invertible. But this 1 minus, if it's, this means that s minus b is invertible. You see what I'm doing? I'm just kind of moving the eigenvalues from 0 and 1 to a and b. So because of this identity, we can always express, so in other words, in general, we know that s minus a is nilpotent, which means that 1 minus this matrix will be invertible, but 1 minus this matrix is just a scalar multiple of s minus b, so that's invertible. And notice that here I'm using the fact that a and b are different. If I didn't have that a and b are different, then I would not have the ability to divide by b minus a here and get a 1 here. Okay, so this is proving this lemma, and now let's go back. So this is invertible, so I can invert it, and I get that wi is equal to 0, which proves directness. So what I obtain from this, if I continue the proof, from this we get that that V contains a direct sum of these W's. Okay, so we've produced these W's. Remember, the Wi are the null space of T minus lambda I to the Ni. Okay, so the only thing that remains is to show that when I take the sum of these null spaces associated to the factors of the polynomial, that I actually get the whole space. Okay, and that's what we're going to use that lemma for, the lemma which tells you about how big the null space of a composition is. This thing. So the point is that because the null space of the composition must be less than or equal to the sum of the null spaces, we get that the dimension of V is less than or equal to the dimension of W1 plus the dimension of WK from the lemma. And that does it. So this tells us that we must have equality. Okay. Okay, so this is, it has a bunch of parts, but the basic idea is that that we've taken the vector space and decomposed it into generalized eigenspaces, and the generalized eigenspaces are all linearly independent from each other. Okay, and right. Okay, so let me just look again at this upper triangular matrix that we started with. Let's say lambda 1, lambda 2, lambda 3, lambda 4, and it has other stuff here. Okay, so the characteristic polynomial, right, is going to be z minus lambda 1, z minus lambda 2, z minus lambda 3, z minus lambda 4. Okay, now you should spend some time with this to figure out what is going on. So, for example, if all of these numbers are distinct, okay, then okay, wait. So I just want to point out a few things before we go to the choice of the basis. So in the case of an upper triangular matrix, right, notice that it's already in, it's almost in reduced, it's almost in row echelon form, right? You have echelons here, but it's just that these are not one, okay? So there's a lot that you can tell about the matrix when you have it in upper triangular form. In particular, you can tell right away if the matrix is invertible. Why? Because if you wanted to put this in echelon form, all you'd need to do is divide the first row by lambda1, the second by lambda2, and so on. So if these numbers, lambda I, if these are all non-zero, right, then you can put it right away into echelon form with ones down the diagonal. And then the rows would all be linearly independent, and the matrix would be invertible, right? So in triangular form, it's easy to tell if the matrix is invertible. Okay, if the diagonal entries, so the diagonal entries are all non-zero, if and only if T is invertible. This is easy to see using row reduction. Okay, but the textbook gives a longer proof, a more conceptual. Well, it's essentially the same proof, but they go through it in detail. So it's like a 1.5-page proof of this fact. But it's obvious from the point of view of row reduction that really the thing that determines invertibility for something of this shape is whether or not some of these are zero. If this was zero, right, then you would be able to eliminate this row by using these two rows. And then you would have a row of zeros at the end, and the matrix wouldn't be invertible. Okay, but this also tells us that if I take T minus lambda, this is going to be like lambda1 minus lambda, lambda2 minus lambda, lambda3 minus lambda, lambda4 minus lambda. Okay, so if I have something in upper triangular form and I take lambda away from it, lambda times the identity, right, then you can see that this thing affects the diagonal values. So remember that when you're searching for eigenvectors, what you're searching for is a lambda such that T minus lambda has a null space, has a non-zero null space. So you're looking at this matrix and you're saying, okay, what value of lambda is going to make this thing have a null space? In other words, for which values of lambda is this thing going to fail to be invertible? Is it going to have a null space, right? So the only way that that can happen is if one of the diagonal entries becomes zero. So you see that if lambda is equal to lambda1, then this row will get killed and will have a null space. If lambda is equal to lambda2, and so on. So this is telling us that the diagonal entries are the eigenvalues. This thing is invertible. So this thing has a non-zero null space if and only if lambda is equal to lambda I for some I. So this tells us that the diagonal entries are the eigenvalues. So putting it into upper triangular form tells us what the eigenvalues are. The problem is that there might be multiplicity, right? So you might have something that looks like this. Right? So you might have a situation where you have multiplicity of eigenvalues occurring on the diagonal. So all you can conclude is that lambda is an eigenvalue and mu is an eigenvalue, but we don't know whether we don't know which power is we don't know what's the minimal polynomial. All we know is that there is a factor of z minus lambda, and there is a factor of z minus mu. Okay. And in the characteristic polynomial, this will be like this, because the characteristic polynomial is always, you have to raise it to the power for how many times it occurs on the diagonal. So this is the characteristic. But the minimal polynomial, we don't know if it could be z minus lambda, z minus mu. It could be z minus lambda squared, z minus mu. There's many possibilities for what the minimal polynomial is. But in any case, we have at least a starting point. We have the characteristic polynomial, and then we can plug that into the decomposition theorem. So we can focus our attention on the null space of t minus lambda 1 to the n1, t minus lambda 2 to the n2, and separately work on those pieces. We could even make it a distributed computation. We could use like a parallel processing. We could say, okay, I figured out what the eigenvalues are, and I distribute each eigenvalue to a different processor, and each processor will work on one of the generalized eigenspaces and figure out what the Jordan basis is. Okay, now so we've reduced it to some kind of algorithmic process in each generalized eigenspace. So the last thing, the last task is in each null space Wi, null space of t minus lambda I to the ni, we find a Jordan basis. Okay, so I'm going to switch to my notes for this, just because there's a lot of notation, and I'm not going to get it right if I handwrite it. And I'll give you the notes afterwards. Okay. I should have two monitors next time I do this. Oops. Okay, so this is just 4 pages. The last page is an example. The third page is how to find the basis. And yeah, the first page is just an introduction. So we have a finite dimensional vector space over a field. We have an operator. It factors into linear factors to powers. Sorry, it's not that it factors, it's that we have a polynomial that kills it. And that polynomial factors into linear factors over the field. This is always possible over the complex numbers. But if you were working on a different field, and if this holds, then we could still find a Jordan form. Okay, so the purpose of this is to explain how to find a Jordan basis, so that the matrix of T in that basis is block diagonal, and the blocks look like this, Jordan blocks. Jordan block with eigenvalue A. Okay, and this is explaining how the basis is a cyclic, in the sense that if you apply T minus A to VI, we obtain VI minus 1. It's this 1 here. So if I apply T minus A, that removes the diagonal, and you're left with this staircase of off-diagonal elements, which are all 1. And so EI is sent to EI minus 1, is sent to E to I minus 2, and so on. So that's the cyclic type behavior. So the first thing we must do to simplify our problem is to apply the decomposition theorem, which tells us that we can decompose V into a sum of generalized eigenspaces associated to the different eigenvalues. And then we can focus on finding a Jordan basis for each of these separately. And then we're going to put them together and we'll get a Jordan basis for the whole vector space. Okay, now for the idea, this is where the complexity comes in, and I'm just trying to explain what the complexity is. So the problem is that for a generalized eigenspace of eigenvalue A, you could have the two following possibilities. Here we have two operators which have the same generalized eigenspace, same eigenvalue A. But you can see that this one has a completely different behavior to this one, because this has a Jordan block of size 3, 2, 2, and 1. And this one has 4, 2, 1, and 1. So if you take a look, for example, this is an eigenvector. E1 is an eigenvector. E2 and E3 are not. They're generalized eigenvectors. But E4 is an eigenvector again. And E5 is a generalized eigenvector. And E6 is another eigenvector. And E8 is another eigenvector. Anytime you have just a diagonal element, that's an eigenvector right there. Whereas here we have only 1, 5, 7, and 8, which are eigenvalues, eigenvectors. So even the number of eigenvectors is actually the same in both cases. This has 4 eigenvectors and this has 4 eigenvectors. But it's completely different because on the left, these two eigenvectors, they are participating in a Jordan block of size 2. Whereas here there's only one of size 2. Anyway, I'm just trying to point out that these two operators, they are different. They're not equivalent or similar, but they have a lot of the same properties. So we need to be able to distinguish between these two. That's the point. Okay, so yeah, so I just write here, T1 has Jordan blocks of size 3, 2, 2, 1, and T2 has blocks of size 4, 2, 2, 1. They happen to have the same number of blocks, but the size of the blocks is different. In general, we could have blocks with sizes making up any partition of 8. Okay, so this is, again, remember what we did at the very beginning of this course. We talked about partitions of sets, and it's the same thing here. The basis is being partitioned into cyclic subsets, and the partitions are different for the two operators. So, okay, so the idea for given T, we would like to figure out how many Jordan blocks there are, what their sizes are, and how to find the actual basis that gives this format. And the idea is simple, that we're going to extract all the information from the sequence of null spaces, T minus A to some power. Okay, so, and we're going to define the dimension of those null spaces to be little ti. So if you just look at this, I'm going to ask for an answer from the audience. So what would be the null space of T minus A? What's the dimension of the null space of T minus A for T1?
4.
4, because it's spanned by E1, E4, E6, and E8. What's the so that means that T1 would be 4 for this matrix. Okay. Okay, and what would be the dimension of the null space of T minus A squared for T1? How many vectors are killed not just by T minus A, but T minus A squared?
Yeah, Andy?
1.
No.
Wait, you said the null space of that squared?
Null space of T minus A squared. So T minus A
is 7,
kills,
yeah.
Sorry?
7.
Yeah, 7. Because this is killed by T minus A squared. This E1 is killed, E2 is killed, E3 is not killed. E4 is killed, E5, right? Because they, T minus A sends E1 to 0. T minus A sends E2 to E1. And then E1 is sent to 0 in the next step. So T minus A squared will kill these two, these two, these two, and this. So it's 2, 4, 6, and 1. So we have 7. Okay, so the next step, T minus A cubed, is going to kill all the vectors in this basis. So when you write the sequence of nullities of T minus A to powers, you get to the 0th power, it's 0. To the first power, it has a null space of dimension 4, then 7, 8, 8, 8, 8. It will be 8 because if you keep raising it to higher and higher powers, it's already killed everything. So there's no one else to kill. It's an 8-dimensional space. Okay, on the other hand, here we have 4 eigenvectors. So T minus A will have nullity of dimension 4. T minus A squared will have 1, 2, 3, 4, 5, 6. T minus A cubed will kill these first 3 basis vectors, but not the 4th one. So it will be 7. So that's why here I've written the sequence of nullities is 0, 4, 6, 7, and then 8, 8, 8, 8, 8. Okay, so I'm just recording what is the growth of the null space when you raise to more and more powers, T minus A squared, T minus A cubed, and so on. That's what I'm recording in the T list of numbers. Okay, and the S is just a convenient thing. The S is well, okay, so this is a kind of crazy formula. You can ignore that for now. But what I'm trying to say is that if you know the growth of the null space, right? If you know that we start with this number, which is 4, if the first number is 4, that tells me that there's 4 eigenvectors, and therefore that there are 4 Jordan blocks. 1, 2, 3, 4. Then I look at what happens next. The 4 jumps to 7. That means that it jumped by 3, which means that there must be 3 Jordan blocks of size bigger than 1. This one, and this one. But I don't know yet how big they are. So I need to go to the next step, right? The next step goes from 7 to 8. So that means that of the larger Jordan blocks, only one of them was of size greater than 2 because it jumped only by 1, right? So in that sense, you see, you can just, it's an arithmetic problem. When you see that it grows by 4, 7, and 8, that means that there's 4 blocks in total. There's 3 greater than 1, this one, and this one. And there's a single one greater than 2, which has to be 3. So you'll conclude that it's 3, 2, 2, 1. Whereas in the other case, it's 0, 4, 6, 7, 8. So that means that there must be 4 Jordan blocks, 2 of them, because it grows from 4 to 6. So 2 of them must be bigger than 1. But then 6 goes to 7. So one of those must be bigger than 2. And then 7 to 8. And one of those must be bigger than 3. So indeed, I have 1, 4, 1, 2, and 2 1s. So just by looking at how it grows, you can deduce how many Jordan blocks there are. Okay, and what I'm saying here, this formula is just a formula for doing that arithmetic as a formula, right? It's saying, if you do arithmetic on the t's, you can figure out what the sizes of the blocks are. And here I found there's 1 of size 1, 0 of size 0, 1 of size 1, 2 of size 2, and 1 of size 3, right? And similarly here. So you can have fun with figuring out how I came up with this formula, but it's elementary. I'm just saying that once you know the growth rates, you'll be able to tell what they are. Okay, so for how to find the basis, right? Once you have that idea, it's easy to find it, but the problem is that it involves many steps. And the problem is that you need to figure out you need to find, for each Jordan block, you need to find what's called a cyclic vector. So for this Jordan block, the cyclic vector is like the seed which generates the rest of the vectors. And that's going to be E3, the third basis vector. Because if you give me E3, then I can apply T minus A to it, and I'll get E2. And if you apply T minus A to that, you'll get E1. So what you're really searching for are the seed vectors, or the cyclic, what they're called is cyclic vectors. And here there will be 1, 2, 3, 4 cyclic vectors. Once you find the 4 cyclic vectors, then you can generate all the rest of the basis, the Jordan basis, from that. Okay, so, right. So in order to phrase this in the simplest way, I introduced a piece of notation which is called linearly independent mod U. So if U is a subspace of V, and if we have some vectors in V, then we can say that they're linearly independent. Of course, we know what that means. But if we say that they're linearly independent mod the subspace, what it means is that anytime you have a linear combination which lies in the subspace, then all of the coefficients must be 0. So it's basically saying that if you were to quotient out that subspace and make it 0, then these vectors would be linearly independent in the usual sense. So what I'm just saying is that these vectors are, they satisfy this condition. So the idea is like this. In the first step, what you need to do is you need to take the null space of T minus A to the top power, the maximum power that is that has a non-trivial null space. Okay, so here, what I'm going to do is I'm going to take T minus A to the third power, and that's going to kill everything. But I want to ignore the things that are killed by T minus A squared. So I want to ignore E1, E2, E4, E5, E6, E7, and E8. I only want the thing which is genuinely killed by T minus A to the third power, not by T minus A to the second power, because that will give me the seed that I need to generate the Jordan block. So you take the maximum power T minus A to the K, mod the null space of T minus A to the K minus 1. And we need a basis for that. This will be the longest lived vectors. All the vectors, it's a basis of vectors that live the longest amount of time. They will survive for K steps. Okay. And so these will be our cyclic vectors for the Jordan blocks of size K. And there's a certain number of them, which has to do with the difference of dimensions between these two spaces. Okay, and if K was equal to 1, meaning that if K, if these are all in the null space of T minus A, then these are all eigenvectors and you're done. The Jordan blocks are all of a size 1. Okay, instead, what you do is you generate everything that is generated by those cyclic vectors. So we apply T minus A to those cyclic vectors, and we get a bunch of vectors in the null space of T minus A to the penultimate power, the power 1 below the maximum. Okay, and then the key point is that the resulting vectors that we get by applying T minus A to these seeds, that these are linearly independent modulo the next layer. And then, okay, and then what we need to do is extend this basis by adding a few more seeds, because there might be a Jordan block of size 2, right? So basically the idea is we picked E3, then we apply T minus A to it and we get E2. Okay, and E2 is killed by T minus A squared, but there are other things now. There are new vectors that are killed by T minus A squared. So we need to add now this basis vector, E5, and E7. So now we have 2 new seeds, but these are not as long-lived as the first seeds that we picked. But we have to add those in, and we continue this process. At each stage, we check whether there are additional seeds needed for Jordan blocks of exactly that size, and we apply t minus a to generate all the progeny of the next generation. Okay, so we end up with this type of a picture where we start at furthest away from the cliff. We find longest lived seeds. Okay, then we generate their progeny, and we check whether there's any additional seeds necessary, right, at that stage, one step closer to the cliff, and we generate their progeny. We check whether we need more, generate the next step, and we continue this way until we fall off the cliff. And then all of those seeds and their progeny are the Jordan basis. And then I give an example here of doing the process. So you can see this upper triangular matrix. You should go through this on your own, and I put it into Jordan form carefully. So I'll put this up on the website. I'll stick around now for 10 minutes of questions. Sorry that I just railroaded you, but I needed to present the whole thing at once. So this concludes our study of the Jordan canonical form. And we're going to go on Thursday to talk about tensors and determinants. And we got another week after, so we'll spend the rest of the time talking about tensors and determinants.
Okay, so Isaac has a question.
Hi, Professor.
Hi.
I just want if there's like any more material we can read on this, especially on decomposition theorem.
I think that the decomposition theorem is actually in the book, in the later chapter, in chapter 8, I think.
I just ran like a text search, and I don't think I have like any result on decomposition theorem.
Well, text search doesn't always work, you know. You got to go
Right.
look at the pages. The type of search that you need is called flip search, not. It's called flip search.
Okay. Okay. Yeah.
Text search is maybe not the best. But the thing is that I'm presenting this in a much more. I'm presenting this in a kind of. It's a little bit of an more efficient way of presenting it, but he goes in great detail and he talks about the null space of t minus a to the different powers, and yeah. So, and I'll put my notes up. The notes, you know, this is a complete proof. So if you go through what I presented in class, it is a complete and rigorous proof.
Okay. Thank you.
Yeah, so the decomposition is in 8b of Axler, if you want to read
Oh,
it.
thanks a lot.
Yep.
I don't have Axler here, so I can't do the flip proof.
Diva, do you have a question?
Yeah, can we quickly go back to the end of the decomposition theorem proof? I'm just not sure which lemma we are using. Like, it definitely feels true. I just don't know which specific lemma that's referencing. The v less than the dim of adding up all the wi's.
Yeah, so this is the point is that this is t minus lambda to the k, t minus mu to the L is equal to 0, suppose. Suppose this was a simplified version, right? Then W1 would be the null space of this operator. W2 would be the null space of this operator. And V is the null space of this product operator. So we are relating the dimension of the null space of a product to the dimension of the null spaces of the two factors. And what we proved in the lemma was that the dimension of the null space of the product is less than or equal to the sum of the dimensions of the factors.
Okay, yes. Thank you. I didn't make that connection at first.
It's okay. So the dimension, so we'll call this one S and this one T. And we're looking at the dimension of the null space of ST less than or equal to the dimension of the null space of S plus the dimension null space of T. That's the lemma that we're using.
All right, thank you.
You're
So
welcome.
Jin has a question.
Yeah, hello, Professor. I have a question about the upper triangular matrix.
Yeah.
Yeah, after we formed a basis of U, how could we know this basis is make it like a triangular matrix?
So okay, so we remember that we start with T over C. So that means that there exists an eigenvalue, lambda. So we take T minus lambda, and we look at the range. Oops, the image of this. And this is our first U. So let me draw a picture of U sitting inside V. Okay, so T minus lambda I. So the first thing that you need to, okay, so right away we're using the fact that there is an eigenvalue in order to show that T minus lambda is not invertible. It's not an isomorphism, which means that the image, the range of it, must be a proper subspace. That's why I draw U as if it's contained in but not equal to V. That's the reason why U is smaller than V, right? It's important. If lambda was not an eigenvalue, then U would just be all of V. So number one is that U, since lambda is an eigenvalue, the dimension of U is less than the dimension of V. So by induction, okay, and that's number one. Number two is that T sends U to itself. U is invariant. Why is that? Well, because T of something in the range always looks like this, T minus lambda of something. This is a general element of U. And this is the same thing as T minus lambda of TV. I'm just using the commutativity. So this means that this here is inside U. So it's obvious that T sends U to itself. So what do we have? We have a smaller space on which T acts. Okay? And then by induction, I'm going to assume that I have a triangular basis for U. We assume, this is the induction step, that we have a basis, let's call it E1, EK for U, which is triangular.
Oh, I know. The E1 and from E1 to EK is a hypothesis for induction.
Is a what?
Hypothesis.
It's a hypothesis. It's
Yeah.
it's the, I mean, we know that we can always find a triangular basis for a one-dimensional space because every matrix is triangular if the dimension is 1. So that means that, you know, we can always assume that we have it at dimension 1. And if we can prove that dimension 1 implies dimension 2 and 2 implies 3 and so on, that's the idea, right? So so then we only have a basis for u. So how do we get a basis for v? We just extend. We just extend to a basis for v. So we have E1 up to EK, and then we have F1 to Fj. And the claim is that it's automatically now going to be in upper triangular form. And the reason is because, you know, T of Fk, let's Fi, right, is equal to T minus lambda Fi plus lambda Fi. So you get a triangular form. This is in U. This is a multiple of Fi. So that's how the proof goes. You show that it's true for V by showing that it's true for a subspace. But the problem is that you need that subspace to be of smaller dimensions so that you can use induction. And the only way to get an invariant subspace of dimension less than the dimension of V is to get an eigenvector. And so we need to use the existence of a single eigenvector in order to make this argument work. And that's why we can only make it work over C. So for example, you cannot take a plane rotation and put it into upper triangular form. There is no eigenvector, so you cannot do that over the real numbers.
Okay, thank you, Professor.
You're welcome.
Howard has a question.
Hi, Professor. So
Hi.
In terms of finding the minimal polynomial, I'm thinking, is it automatic from the Jordan form?
Yes.
So just observe the Jordan blocks and then.
Well, yeah. So actually, maybe I'll just go back to the notes because they're. You see, when you have a Jordan blocks like this, when the Jordan blocks are like this, T minus A will kill this, 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 and this.
Yes.
Okay, but it will not kill this, this, this. I mean the basis vectors corresponding to these columns. So it will not kill E2, E3, E5, and E7. So then I try T minus A squared. That will kill most of them, but it won't kill E3. But then once I do T minus A cubed, then it kills everything. So that's why I know that I've got the minimal polynomial. So the minimal polynomial for this matrix is T minus A cubed, because the biggest Jordan block has size 3. Okay? Whereas here the minimal polynomial is T minus A to the 4th power. You see how, so the characteristic polynomial is T minus A to the 8th power in both cases.
Yes.
So the characteristic polynomial tells you the eigenvalues and the total multiplicity. It tells you the total dimension of the generalized eigenspace. But it doesn't tell you how that generalized eigenspace breaks up into cyclic blocks. In order to figure that out, what you need to do is compute the dimensions of the null spaces of T minus A to the different powers. You literally have to compute each one separately, the null space of T minus A squared, T minus A cubed, and that will grow until you reach the dimension of your subspace. And then you know that you can stop. And you'll know what the degree of the minimal polynomial is. So that's why finding the null space of a given matrix is so important. That's why the earlier part of the course was devoted to finding a basis for the null space, because you need to do this several times in order to classify your operator. You needed to do it for T minus A squared, and so on. That's what I do here in the example. I compute the null space of T minus 1 the null space of t minus 1 squared and the null space of t minus 1 cubed. And then I have already 5 dimensions, so I know I can stop because the matrix is a 5 by 5 matrix. Okay, and then once we know this, then we need to pick the Jordan, the longest lived elements, right? So I find the cyclic vector for the Jordan block of size 3. That's the first thing that I need to find. Okay, that's E5. And then I apply t minus 1 to E5 to compute its progeny. That's E1 plus E2 plus E4. That will be a basis of the t minus 1 squared null space modulo t minus 1. But then we need to add an extra thing because there turns out to be a Jordan block of size 2. And we get a cyclic vector for the Jordan block of size 2. And then we, the thing of size 3 will generate something of size 3. The thing of size 2 will generate something of size 2. So I have a total of size 5. And then if I put those two together, this will be my Jordan basis. The Jordan basis will be E1, E3, E2, the sum of E1, E2, and E4, and then E5. And then if I write the matrix in this basis, then it will be a Jordan 5 by 5 thing with 2 blocks, one of size 3 and one of size 2. That's clear, right?
I understand. Yeah.
Okay.
Thank you.
Professor.
Hi.
Just hello.
Last question.
Yeah. Okay. So for number of eigenvectors, is there some way that we can find out the number of eigenvectors, or do we just have to compute them by hand using the eigenvalues?
Well, the first thing is to figure out, in order to find out which eigenvalues occur, you need to look at t minus lambda, and you need to figure out when does it fail to be invertible, like when does it have a null space that's non-zero. But then you need to, so that will tell you the eigenvalues, and that will guarantee that there's at least one eigenvector for each one of those numbers. But then in order to figure out how many eigenvectors there are for each eigenvalue, you need to compute the null space of t minus lambda. So the t minus lambda will be some matrix. You need to compute the null space, just like we did in those previous exercises. When you computed the null space of the matrix and determined the dimension, found a basis for it, that's exactly what you're doing in the case of finding how many eigenvectors there are. You need to know the dimension of the null space of t minus lambda. That dimension is the number of eigenvectors for that eigenvalue.
I see.
There's no shortcut to finding it.
Yeah. What's it called? Concerning the quizzes, there was no, last week's quiz was not updated. I remember that there was a problem with one of the questions and you said you would update it. It wasn't for everyone.
Okay,
Same
I'll
for, I
check
think,
that,
one-
but I did update it, but I'll check it again.
All right. What's it called?
Okay.
Yeah, last one. I emailed you about this. I had a solution for one of the questions.
Yeah, I'll
but
deal
it
with
was
that
like-
later. I'll deal with that later, yeah.
All
Thanks
right.
for reminding me. Bye, everyone. Thanks, Syed.